This is the recording for the remaining slides from Chapter 9, dealing with volcanoes. We left off talking about intrusive igneous activity. Intrusive meaning that it's happening inside of the Earth, because hopefully you remember back to the beginning of the semester when we talked about rocks that were formed through igneous activities. And many of them were actually formed at depth. So most of our magma is going to harden at depth and it's not going to erupt as lava. Because of that, it will crystallize at depth without explosion, causing very different features than the flows that we've looked at so far. And I'm sorry, I'm on the wrong slide. Let me back up one moment. So I was mentioning that most of your magma is emplaced at depth. A large underground igneous body, if you want, you can think of this as a large kind of solidified lake of magma. It's called a pluton or an intrusion. And these plutons are going to be classified according to their shape and their orientation with respect to the host rocks or the rocks that are around them. Their shape is usually classified as tabular or massive. The tabular ones are sheet looking, like you kind of can see in the picture here. The massive ones are going to be more, we'll see in a few minutes kind of what they look like, but they're going to be much more like a solid, large, rounded rock as opposed to looking like sheets of rock. With their orientation in respect to the host rock, they can either be discordant, where they're cutting across existing structures, kind of like on an angle or a diagonal or a perpendicular line, or they may be concordant, where they inject parallel to the features, kind of like separate layers would be in a sedimentary rock. And now back to the slide. We can then further classify these groups. So a structure called a dike is a tabular discordant pluton. They are found in parallel groups to each other, but they are going to be discordant compared to the regular rock around them. Sometimes they are the result of erosion from a previous volcanic neck. So that structure that brought the magma from beneath the volcano up so that it could erupt as lava. They can also occur as sills, which are tabular concordant plutons. They look kind of like buried lava flows. And they may exhibit columnar jointing, which is our third category listed here. Columnar jointing are very interesting structures, as you'll see in 2 slides when we get to a picture. They were originally pillars or pillar-like columns, and they generally appear to be 6-sided. And as they cooled, they shrunk a little bit. So these were like pillars of magma that shrunk, contracted as they cooled. They have a fine-grained texture. Columnar joining may be a little bit deeper than the other 2 features. Dikes and sills in general are shallow features of igneous intrusive activity. And this is showing you here what the dike looks like. You can see the picture on the right-hand side of the screen. It is perpendicular to quite a bit of the other rock activity in the area. And this is showing a picture of a dike from Colorado. The picture of the sill, you can see that it is parallel to the sedimentary rock features there, and that is a sill from Utah. And here we have our columnar jointing. If you look at them, you can see that they are roughly six-sided features. Some of them that is more clear than in others, and that six-sided effect is due to the rapid cooling of this magma. It causes shrinkage, and with the shrinkage, you can see in some of them it has also caused cracks to form. What is strange to me when I look at these features is that these look like things that were man-made. These don't look like a volcanic feature from the cooling of magma, yet they are a result of that. To me, they look like somebody's patio built out across an area or paver stones being used, but these are the result of a natural activity. There are a few other types of igneous activity, intrusive igneous activity that we should mention. One is a laccolith. This one is a lens-shaped mass, and it can actually, when it forms, it may go underneath other layers, pushing the strata above it up and kind of curving them over top of it. And it can then lift the sedimentary strata that it is penetrating through. These are usually associated with a central magma body, and there may be branching offshoots that form other laccoliths as well. The laccoliths are going to be smaller than the batholiths. The batholiths are your largest intrusive bodies. They're often found in groups, which does make sense because where you have a lot of igneous activity, you have a lot of igneous activity. These are not going to be just volcanoes found randomly spread all over the place. They're going to be centers of volcanic activity. A batholith is kind of your largest structure. They can be several hundred kilometers long and over 100 kilometers wide. When they're exposed at the surface, they can be upwards of 1,000 square kilometers. Sometimes you'll find ones that are smaller than this that are referred to as stocks, and those are just a smaller batholith structure. They tend to be composed mainly of granitic structures, felsic and intermediate rocks. And batholiths may be the structure that underlies a volcanic mountain. We can see a laccolith structure here, and you can see what it looks like above ground as opposed to what it looks like when we look at the geologist's sketch here. So you can see that the laccolith is coming off of this larger stock structure, which is a small batholith. And then Mount Ellen next to it would then be a batholith or a stock structure here. And it is worth remembering that these structures that look like mountains, that we would classify as mountains, are really extinct volcanoes. This gives you a better idea of some of these igneous intrusive bodies and how they can relate to each other. So you can see these magma bodies as they solidify become plutons, but you can see where there might be fissure eruptions, pipes, sills, laccoliths, dikes, all of these structures related to then also your composite cones and your cinder cones. And as they are uplifted, as the ground around them is eroded away, these are the structures that you get to see because these are the more resistant to erosive forces than perhaps the surrounding materials are. Finally, the global distribution of where we find igneous activity and therefore volcanoes is not random. Most volcanoes are located on the margin of ocean basins. So margin being these areas where two things are coming together usually. And the ones that are found on the margins of your ocean basins tend to be intermediate or andesitic in composition. Those that are confined at the deep ocean basins tend to provide your basaltic lava flows. And then the third group are those found in the interior of the continents. We're going to see briefly how these look. This is showing you the ring of fire. The volcanoes that you see here going around the Pacific Ocean also go around a pretty similar, if you remember back to the earthquakes area, of where we can find a lot of activity. And this activity is related to continental plate movements and the subduction zones of your oceanic crust. There is this very clear ring of fire around the Pacific Ocean where there are a lot of composite cones and a lot of volcanic activity. A lot of islands around this area have been formed by volcanic activity over the years. You have the islands coming off of the coast of Alaska. You have Hawaii, the Galapagos Islands, Easter Island, Tonga, New Zealand, the Indonesian islands, Japan. All of these are the result of volcanic activities. The plate motions provided the mechanism through which the mantle melted, produced magma, and then the cracks and the fissures produced ways for that magma to come to the surface to form new land structures. As I just mentioned, the plates are providing the mechanism for rocks to melt. They're going to melt because of the subduction. And as the one plate subducts under the other, we're going to have partial melting occurring at these convergent plate boundaries. That descending plate is going to partially melt because part of it is going to still be cool. And as water is driven up off of the plate, we're going to see melting occurring. From that melt, the magma is going to rise upwards. And then you can form volcanic island arches like the Aleutian Islands. And over time, through the motion of plate tectonics, these volcanic arches can become part of the continental crust, such as happened with the Andes Mountains. We can also see igneous activity occurring at divergent plate boundaries, like we find in the mid-Atlantic ridges. These are where we're going to have much of that basaltic material occurring. And this is where we see the largest volume of volcanic rock produced. This is where your lithosphere is pulling apart. And as it does, there are cracks and fissures. The magma is going to come up and solidify inside of those, growing your ocean crust. Partial melting will be occurring at this place. And most of these are going to happen at the axis of the ocean ridge. 60% of the yearly magma output with the ocean ridge system is associated with seafloor spreading. So this is where we're going to see most of that new creation of magmatic rock occurring. And then finally, there can also be some intraplate igneous activity. This can occur within a rigid plate where a plume of hot mantle material rises. The depth of that mantle plume is a topic of debate. Large plumes are called superplumes, and they tend to form in localized regions called hotspots. Now, Hawaii really is the result of hotspot, yet it does seem to fit inside of that ring of fire area. The Columbia River Plateau is also a part of this. What happens is that your continental crust, well, your crust for that matter, is moving over a hot spot underneath in the mantle. So the mantle has a hot spot. It is going to be rising magma up through the crust, forming new structures. We don't quite understand all of the mechanisms involved with this. There is a suggestion that there could be a relationship between hotspot activity and some past extinction events from a biological perspective. This is the end of chapter 9, but we're going to be continuing through to chapter 10, which deals with crustal deformation and mountain building. So this is going to go directly along with chapter 9's information. Before we start with mountains, we need to talk about what we mean by deformation. So deformation is kind of a general term that refers to all the changes in the original form or size of a rock body. So you're taking a rock and you're changing it. That change is a deformation of the rock. Most crustal deformation happens along plate margins, those plate boundaries, where there is subduction, where there is growth with new rock being created, where they're sliding past each other and kind of breaking each other down. Features that form through deformation are rock structures or geologic structures, yes, but they're going to form differently than just the solidifying of rock or the solidifying of igneous rock, the compaction of sedimentary rock or things like that. We're going to form features differently through this. Not surprisingly, some of this is going to be related to metamorphic activity, but really we're going to be talking about folds, faults, and joints as we go through. So hopefully, if you remember back to when we talked about rocks, we talked about stress. Stress was one of the things that led to metamorphic rocks. Stress is a force that deforms rocks. It can change them. And stress was related to foliation in rocks. I'm going to assume you remember that idea of confining pressure and differential stress. Confining pressure dealt with stress being uniform in all directions. The differential stress was that stress was unequally applied in different directions. And we can talk about different types of stress. Compressional stress is when you squeeze a rock like you would if you were putting it in a vise. This is what happens at convergent plate boundaries. This is the process that makes mountains. We have tensional stress, where you're pulling apart a rock to elongate it. This is what happens at divergent boundaries. And then we have shearing stress. This is going to cause the sliding and the tearing because you're pulling different portions of the rocks in different directions. This is the result of the movement of one plate past another plate. And a couple other words we should kind of define before we really get started. And one is the word strain. A strain is a change in shape of a rock caused by stress. The rock is going to lose its original configuration and it is going to be deformed. Strain is the result of a deformed rock. So how can we deform it? Elastic, brittle, and ductile tend to be our three terms for this, and we will do our ductile and brittle activity on Thursday. It's a very, very short activity. Elastic, think of a rubber band. Your changes are things that are recoverable. When you stretch a rubber band, it's going to return to its original place, size, shape, etc. when you remove the stress. This is like an earthquake deforming things. Brittle. That's what the jackhammer picture is there for, or smashing something with a hammer. The rock is surpassed its elastic limit. It's going to have to bend or break. It's going to create smaller pieces of the original rock. It will break some chemical bonds as this happens. And then we have ductile. Ductile is going to be a change in shape, but with no fractures. You're not going to get smaller pieces. Your pieces are just going to look different than they did when you started. This is showing you the picture of a quarter that was run over by a train. But this could also be, I'm sure you've seen at lots of different attractions, they have the machines where you put a penny in and then a couple quarters and you decide what picture you want on the penny. And you turn it and out pops a penny with an imprint of an image on it. You usually see these at zoos and aquariums. That is a ductile change. It's coming out a completely different shape than the penny started, but it's still a penny. May not spend as well when you go to the store, but it's still a penny. This slide probably looks really familiar to you. The factors that influence the strength of a rock are the same as they were when we started this semester. Temperature. Rocks at high temperature tend to be soft and malleable. They're going to deform through ductile movements, through flowing or folding. A low temperature rock, they're brittle. When they deform, they're going to break. Rocks dealing with a lot of confining pressure are going to bend rather than fracture. So lots of pressure on top of them is going to lead to bending. Because confining a rock actually makes it harder to break, because that confining pressure makes the rock stronger and more prone to flow, bending. The rock type is going to change the strength of it too. Sedimentary rocks overall are more ductile, and igneous and metamorphic rocks overall are more brittle. So we will see difference in what is going to deform well or not deform and instead break based on the rock type. And then time is going to play a role too. Changes that are very fast are generally going to shatter rocks. They're going to respond in a brittle manner. Whereas changes that are very, very slow can respond in a more ductile manner, where there'll be flowing or bending of the rock. And these are overall generalizations. This may not be true in every single circumstance, because you will find igneous rocks that become ductile and metamorphic rocks that become ductile. And you will find sedimentary rocks that break. But these are generalized overview ideas of how the different factors can influence rock strength and whether or not it will act ductilely or brittly. More ductile or more brittle might be the better words there. So the first main idea before we get to real mountains are folds. Folds are going to result in rocks that are bent in a series of ways. Folds are the result, mostly, from compressional forces which shorten and thicken the crust. So you're pushing it together, you're shortening the crust, and as a result, it's going to thicken the crust because the rock needs to go someplace. And if it's being squeezed together, the only place for the rock to go is to go either upwards or downwards. So the rock is going to fold. Your horizontal surfaces are now bent as a result of permanent deformation. The layers are going to be bent around an imaginary axis. And this axis is called the axis plane, the hinge, or the hinge line. The rock structures that come off of that axial plane are the limbs. So those are the sides of your folded strata. So we can see rocks that are bent into a fold here, the axial plane, and the two limbs coming off of it. This one looks pretty simple. Now here you can see at the top, the axial plane and the hinge line, what it looked like before erosion, and what it looks like after erosion. So we've eroded away the top of our mountain here. We've eroded away the top of the mountain or the hill here. And looking at the ground surface, everything would look level. You would not have known that there had been a fold here until you looked at a cross section of the ground. And then you would be able to see that your layers were not straight across. They were not parallel to the ground surface. That in fact your layers were curved. This curvature of the layers underneath is going to be really important in determining what happened here in the geologic history. As a matter of fact, many of the ideas we talk about in chapter 10 are going to come back up in chapters 11 and 12, looking at geologic history and figuring out the age of the earth and how different historical processes occurred throughout the formation of Earth as we know it today. And this picture is great. And these pictures do show a very generalized idea. But sometimes you probably think, well, how well does this cartoon picture represent what happened in real life? Oh, there you go. Here we have a picture of what happened in real life. If you look closely at this picture, you can see folds. But this one is really, really complicated. There's a number of different folds occurring here. As a matter of fact, there's even a fault running down the one side. We have both anticline and syncline folds here. Your anticline are your upfolded or your arched rock layers. The syncline are the downfolded rock layers. So an anticline is going to have the point of the fold pointing upwards towards the ground surface, and the syncline is going to have it pointing downwards towards the next layers of the earth. So anticline points upwards, syncline is going to point downwards, and the rock folds. These are not our only types of folds. These are our main two types of folds. They can also be further divided. Anticlines and synclines can be, both of them could be symmetrical, meaning that the limbs are mirror images of each other. They can be asymmetrical, where the limbs are not mirror images of each other. Those two make pretty good sense. And you can see the symmetrical and the asymmetrical as the first two shown in the picture below. They can also be overturned. When one of the two limbs is kind of folding over the other like an ocean wave, that limb is tilted beyond that vertical line. They can also be recombinant and plunging. In a recombinant fold, the axial plane has come back to horizontal. And in a plunging, the hinge is going to be beneath the Earth's surface. This is showing you the symmetrical folds here, the asymmetrical, and the overturned. Now, looking at these pictures, you could probably pick out the anticline and the syncline in the first two pictures. That third is not something you would have easily picked out, but if you look at those, will look like grooves in the rock, you can actually start to see where there were the results of folds. This is showing you that plunging anticline from a picture in Wyoming. And remember that plunging anticline happens when the fold is going to die out, that it penetrates back into the Earth's surface. And then there are a few other types of folds. We have domes and basins. Both of these are circular or slightly elongated. They differ in how they displace the rocks. Domes are an upward displacement, so this is going to form a hill. Basins are a downward displacement, or a hole, kind of a pond or a lake in the ground. And because of their different types of displacement, the rocks that are in the center will be quite different. In a basin, your center rock are your youngest strata, your youngest layers, and the oldest are around the edges. Whereas with a dome, the youngest layers are at the edges, and the oldest strata are actually going to be in the core or the center. This is showing you a dome structure from the Black Hills of South Dakota. You can see Mount Rushmore is here in Harney Peak, structures you may have heard of. The core in this structure is actually a Precambrian, igneous, and metamorphic rocks. So you have the granite and the schist there. And surrounding it are the younger sandstone and limestone features. So you would know that this is a dome in part by looking at it, because Mount Rushmore and those areas around it are going to be higher than the surrounding regions. But because those rocks are also much older, you know that this fold is a result of a dome structure. And here we have Michigan. This is showing you a basin. Our youngest rocks are actually in that yellow and yellowish green, well, I guess perhaps lightest green color. And then as you go towards the purples, the reds, and the orange, the rocks are getting older. So this is a basin structure formed by a fold. Another type of fold, and this is going to be on par with a syncline and an anticline, is a monocline. Monoclines are coupled with fault structures. They are large step-like folds in what otherwise is a horizontal sedimentary strata. They're due to ancient dipping reverse faults located in the adjacent rocks. What happens is that one of the rocks moves upwards, and the rocks that are on top of them just kind of are going to drape themselves over it the best they can as they form. So you get a one-sided fold here. The one level, the one side of the fault is going to move, and it would look like a fold. However, the result of the fold here is due to plate movement activity, as opposed to just that idea of confining stress. This is going to look sometimes, especially when you look at this picture, like a ridge structure as opposed to a real fold. because you're only going to have it on the one side. Faults are designed as fractures or breaks in a rock. And along a fault, there's going to be some amount of displacement that has taken place. How much displacement? It could be very little. It could be hundreds of kilometers or more. You can see in the picture here where that fault or that what looks like a crack is in this rock. You can look at that one layer, well, multiple layers here, to figure out the offset. And you would measure that offset being the distance of displacement that has happened along the fault. You can measure it, and you can also figure out the direction that the rocks have shifted. So one has shifted downwards, the other has shifted upwards in this picture. And the offset, well, the offset doesn't look like very much. However, as I'm guessing, this is not a small rock picture, and this is actually like the side of a cliff or something. It actually could be meters of displacement as opposed to the few centimeters it may in fact look like. There are a number of different types of faults that we're going to mention. I know you're all like, wait, I thought we were doing mountains. Promise, we're getting to mountains soon. One of the types of faults is a dip-slip fault. Movement is going to occur along an inclination called the dip of a fault plane. There are two walls involved in this dip-slip fault. One is the hanging wall, the other is the foot wall. The hanging wall is the rock above the fault surface. The foot wall is the rock below the fault surface. This may result in rocks moving up. So when that happens, your hanging wall is going to move up the foot wall, as you see in this picture here. When you look at that pink layer, the foot wall pink layer is much deeper than the hanging wall layer, because that hanging wall layer has actually moved up the fault. Through erosion, it looks like they are both flat. However, when you were to compare the different ground layers, you would see that really this structure has moved, that the hanging wall has moved in relation to the foot wall. It could also be that the foot wall sunk along the fault line, and generally in some of these circumstances, you'll see movement from both of the walls involved on this fault. There are now multiple different types of dip-slip faults. The first is a normal one. In a normal fault, the hanging wall block is going to move down the fault, moving down your footwall block. So the footwall block stays stationary, that hanging block is going to move down. These are associated with the formation of fault block mountains. They cause tensional stress as this happens, which lengthens the crust because it's pulling the rocks away from each other. These are prevalent at spreading centers. This is what you would find occurring in Iceland. And the tensional forces are going to be the big forces in play during these movements. The features that are going to be related to these normal faults are horse, which are really uplifted fault blocks. Grabens, which are downdropped fault blocks. So you're going to find generally those two structures together, frequently next to each other, where you have the up ones and the down ones directly next to each other due to the resulting movement of the footwall and the hanging wall. You may also find half grabens. These are when your fault blocks are tilted. There may also be a detachment fault that is going to look in this picture kind of similar to what could become a slump zone. So you have these slopes of these normal faults joining, and as they join, they eventually form a nearly horizontal fault under a larger portion of this faulting field, if you would. These are all your normal fault features. Then you can have reversed and thrust faults. If you're thinking, wait a minute, we talked about some of these already in earthquakes and volcanoes. Yes, chapters 8, 9, and 10 have quite a bit of overlap in vocabulary. In a reverse or a thrust fault, what's going to happen is your hanging wall is going to move up your foot wall. When I gave the example at the beginning of this dip slip fault, I gave the example of a reverse or a thrust fault. This is also going to cause stress, but it's a different stress. This is going to cause compressional stress. It's compressional because you're pushing your rocks together. In a normal fault, it was tensional because you were pulling them apart. But in a reversed and a thrust fault, it's compressional as you push them together. This is going to cause a shortening of the horizontal area of the crust, and mountains are going to be a resulting feature. This is most pronounced at continental plate boundaries. So where India hit Asia is a great example of this type of compressional stress. A reverse fault is when that dip is greater than 45 degrees, that dip slip fault. A thrust fault happens when the dip slip fault is less than a 45-degree angle. This is showing you a thrust fault here. Remember that dip is less than a 45-degree angle. And you can see that here, that it is less than a 45-degree angle. Slightly less than a 45-degree angle in this picture. This is looking at the compressional stress from a thrust fault. You can see that there are a lot of folds that are forming in here. And what happens is that the crust becomes thicker and shorter. The result is the creation of mountains. This is where you have two plates coming together. And as they do, because in this picture they're both continental crust, neither of them is going to want to subduct under the other. So instead, they're going to compress and mountains are going to form. We can also have strike slip faults. If you're thinking, once again, wait a minute, we talked about these already with earthquakes, you're correct, we did. In a strike slip fault, the strike is the fault surface. Your dominant displacement is horizontal and parallel to that strike. So things are going to be moving past each other as opposed to away from or into each other. Transform faults are your large strike slip faults that actually cut through the lithosphere. They tend to make up a lot of your plate boundaries. There may be a zone of parallel fractures rather than a single fracture associated with a strike slip fault. Movement along this fault may result in earthquakes, and movement tends to not necessarily be along the entire strike slip fault when movement occurs. It may still happen in a very small zone of your strike slip fault. One of the structures that can result from faults are joints. Joints are very common structures. If you're thinking, literally, we just talked about columnar joints, you would be correct. We just did in chapter 9. We talked about sheeting joints in chapter 4. Joints happen where fractures, where there's no, along fractures where there's no appreciable displacement. Most tend to form when rocks in the outermost crust are deformed. And these are what is left behind. These tend to be far more resistant to erosion than what was around them. They tend to occur in groups, but they can be random, and they can also within a group be random in their orientation, meaning that some are in one location, some are in another, and they may run not necessarily parallel or perpendicular in a very random or patchy structure. They tend to be really important for mineral deposits, but they're very problematic for construction. They tend to be very resistant rocks, and they are random frequently in exactly where they are. So it makes doing construction in an area with jointing quite difficult. This is a picture here of Devil's Tower. Devil's Tower is 1,265 feet above the surrounding grassland and pine forest in Wyoming. It is a columnar joint. It was actually the nation's first national monument, established in 1906. It's beautiful, but it looks entirely out of place where it is here. This is the result where there was a fracture in your between your plates, likely, or within a plate, and no real movement happened. So because of that, in this being it's a columnar joint, it was filled by magma, and this was the resulting structure. This is a picture of parallel joints from Arches National Park in Utah. These are the Navajo sandstone structures. So joints do not have to be large columnar joints like we just saw. They can also be parallel joints, which are a lot smaller in structure, but are still the result of where there was a fracture with no displacement, and rock structures then formed inside of that fracture. Now that we know a little bit about folding and fracturing, we're ready to talk about mountain building. The process of producing a mountain belt is orogenesis. Perhaps not the word you expected. I remember the first time I learned it, I was like, wait, what? Orogenesis? The genesis makes sense, their creation. Oro didn't make sense for me for mountains, but this is what it's called. Most mountain building is going to tend to occur at convergent plate boundaries. This is going to form compressional mountains. These are going to contain large quantities of pre-existing sedimentary rock and crystalline rock. These rocks are going to be faulted, contorted, folded, and pushed into mountains. There's going to be varying degrees then of metamorphic rock and igneous and sedimentary rock present. The amount of deformation could be related to then the amount of metamorphic rock you're going to find in these structures. These compressional mountains, you can see in this picture here where the old mountain belts are and where the young mountain belts are. You can also see shields and platforms. When you look at the mountain belts, they are related to plate boundaries, either current or past plate boundaries. The Appalachians, Caledonian Mountains, and the mountains of the Greenland Shield When you put all of those together, you find mountains that existed due to Pangea. The Urals and the Altai-Sayon mountains are the result of Europe and Asia becoming a singular continent. Many of the mountains shown here in red are the result of recent plate movements. Well, more recent than the others, so things less than 100 million years ago, which for most of us doesn't count as recent, but geologically, very recent. You can build mountains through other structures, through other processes. And if you're thinking, wow, this looks exactly like what we just did, yes, island arc type mountain building is going to be related to what we talked about in chapter 9, with the subduction of the oceanic lithosphere, the partial melting then of the crust, producing magma that comes up through the crust surface and produces islands. The subduction of the oceanic lithosphere is the driving force here in mountain building. It's not that compressional force of two things moving together. It is two things moving together, but it's a subduction force. There will be periods of volcanic activity related to this, and igneous plutons are created at depth, and there's an accumulation of sediment due to the subducting plate that helps to create the new crust above this area of melting. Volcanic arches can be carried by subductive plate movements to continental margins and then can become part of continental margins during mountain building processes, like the Andes Mountains on the coastline or next to the coastline of South America. This is also seen in the western Pacific coast of North America with the mountains that are on the edge of Alaska, Canada, and the continental US. Then there's really the Andes type mountain building. While the Andes Mountains are formed in part by magmatic activity, they're a special type of this occurring at the oceanic continental crust convergence. As opposed to forming the Hawaiian Islands, where it's an oceanic subduction, where the Andes are forming is an oceanic continental subduction. So you have your oceanic plate subducting under a continental plate. This is going to create long-lasting magmatic activity, and it's going to build continental volcanic arches. There's going to be a resulting crustal thickening from this. This is generally something seen on passive margins prior to the formation of a new subduction zone. It can be found on active continental margins when your subduction zone is formed and there's a deformation process happening. So what happens is your continental volcanic arch is going to form off to the coast, off to the side of the coast. The oceanic lithosphere is going to descend into the mantle, where it increases in temperature, melts partially, and is then going to be driven up as magma to the surface. Batholiths are going to form, and the continental crust is then going to continue to form as magma ascends through it. It's going to create plutons and batholiths, which eventually become uplifted and eroded. An accretionary wedge will form. These are unconsolidated sediments on your subducting oceanic plate that are going to be pushed onto and kind of plastered onto the continental plate that they hit. So up until now, we might have just been talking about the formation of islands. But once these accretionary wedges form, you're going to use the oceanic plate to push these, what had been islands, onto a continental crust. The wedge is going to trap sediment between itself and the continent. Usually sedimentary rocks are going to be trapped inside of there, and that is going to create the four-arc basin. This is not just seen in the Andes. This was also seen in the Sierra Nevadas and the California coastal mountains. So you form them as islands, island-like structures in the ocean. As subduction continued to happen, they were pushed towards the continental crust, where they eventually became part of it. Like we see happening right here. So it's a passive boundary. There's then subduction with lots of igneous activity, and uplifting is going to follow with more subduction. And these mountains then become part of the continental plate structure. You can also have Cordilleran type mountain building. This is associated with the Pacific Ocean as well. The Pacific Ocean, it says like the Pacific-like ocean that may never close. From a geological perspective, the Pacific Ocean may never really close. It is very large, and while it is shrinking, it may never fully close. There are island arcs, though, that as it shrinks will collide with active continental margins. The collision and accretion of these fragments will then add them to your continental margins. And your mountain belts here will be generated when one or more of these crustal fragments collide with the mountain due to subduction. So not being pushed, but due to more subduction. They're going to be peeled. If they're from a terrain, they're going to be peeled off of the descending plate. And different collisions will happen over time, pushing things further and further inland. This is kind of what's happening here. Microcontinents and volcanic islands are carried towards a subduction zone. They are too buoyant to subduct. They're going to then become, plastered really is the best word for this, onto the continental plate that is there. I know you're probably thinking, this sounds really, really, really familiar to what we just looked at. Let's go back for a moment. Here you have a passive margin with a trench of subduction. There's a lot of sedimentary rocks here. At the subduction zone, melting is going to create a volcanic arch, which is then going to follow with a period of uplift as the mountains are kind of being added on here. The mountains are actually occurring on part of the continental crust. There may be some that are going to be added onto through processes that will happen with islands offshore, but a lot of what we're going to be seeing is due to magmatic activity on the crust itself. Whereas the building of the crust here is entirely due to the addition of island material. I want to be sure that I was clear on that. This Cordilleran type mountain building is going to be to the addition of the island material, whereas the Andes type is going to be to the addition of magmatic activity onto the continental crust that's already existing. I don't think that was clear. If we need to talk more about this in class, we will. This is looking at a structure, the North Amalian Cordelia, that is the result of the mountain building we just talked about, where this was added on as different microcontinents and different islands that were accreted onto or plastered onto the continental crust here. You can see in this picture where there are modern day oceanic plateaus and fragments. The Galapagos Rise. A couple different plateaus are here. The Hawaiian Ridge, the Caribbean Plateau, the North American Igneous Province. Lots of different structures that may become part of what we think of as real continents in the future. But let's look at one you're far more familiar with. Continental collisions causing mountains. Is your alpine type mountain building. Two plates, both with continental crusts, are converging. The Indian and the Eurasian plate are our most common here. This is the resulting formation of the Himalayan mountains and the Tibetan plateau. This is going to be characterized by shortening and thickening of the crust due to folding and large-scale thrust faulting. Where these two things come together is called a suture. So sutures where your two continental plates become welded, sewn together. There may actually be portions of the oceanic crust that are crushed inside of there that can be used to help identify the exact suture location. So what happened here is that India moved north, while Asia was moving south and, hold on for a minute, east. Yes, southeast. So India was moving basically due north as Eurasia was moving southeast. They collided into each other. And the result of this collision is that India became sutured on, and it created the Himalayan mountains, and behind that, the Tibetan plateau. India is still moving north. Asia is still moving eastward, with portions of mainland Southeast Asia moving southeastward. But if you look here, India remained intact. Asia was deformed. Southeast Asia is relatively young compared to India. And because of that, when it deformed, it formed smaller crustal fragments. It was still relatively warm and weak compared to the Indian rocks. So it was ductile and it was able to move, and it did. So the resulting structural move was mainly done on the part of Asia because it was a younger, more ductile rock, whereas India was an older, less ductile rock, so it actually stayed more intact during this movement. So here we can see India is pushing towards Asia. There's a subduction of the oceanic crust, and eventually the Indian-Australian plate is going to suture into the Eurasian plate. There may still be some structure there that is oceanic structure. That ophiolite structure may contain some oceanic crust that did not subduct. You can see the suture line would then be right there between those structures. The Appalachians are actually the result of three different periods of mountain building. The first happening 750 million years ago with Rodinia, where you have active volcanoes between North America and Africa. About 600 million years ago, plate motions changed, and an ancient ocean started to close. You can see that in A, we have a volcanic arch area and a microcontinent between North America and Africa. As the ocean, that ancient ocean closed between the volcanic arch and North America, that old volcanic arch became part of North America. It is tectonic orogeny, so that is coming from those tectonic volcanic arches. This happened about 450 million years ago, that the tectonic orogeny became part of North America as the volcanic island arch became part of us when that ocean closed. About 350 million years ago, the Akkadian orogeny happened with the collision of of a microcontinent with North America. There was thrust faulting, metamorphic rock, and an infusion of granite from this microcontinent that added significant width to North America that wasn't there previously. So that Avalonia microcontinent becomes part of North America. Then about 250 to 300 million years ago, Africa and North America collided, deforming both of their crusts. This is the Alleghanian orogeny. So the formation then of additional mountains from the colliding of these two massive continents. This broke up about 180 million years ago. And when it broke up, part of Africa remained welded to North America. Three distinct periods of mountain building. Your tectonic volcanic arch, the Avonian microcontinent, and then the mountain building as the result of a collision with Africa. The Alps and the Urals formed very similarly to this, with multiple rounds of mountain building due to plate tectonic movement. This is showing you part of the Appalachians, and you can see here that there are very distinct regions as you go from the Appalachians out to the coasts. You have your valley and ridge system, the Blue Ridge Mountains, the Piedmont, the coastal plain, all of which have very distinct geologies, soils associated with them, and they are the direct result of this mountain building activity. One of the last topics we need to mention is buoyancy and the principle of isosity. Isosity deals with the concept that you can see in this picture here. You have a floating crust that's in some form of a gravitational balance. When it is changed, you get an isostatic adjustment. So when you remove weight from the crust is going to have to uplift to continue to float. When you put more on the crust, it is going to actually sink because it's dealing with more weight. So there has to be a gravitational balance, and that's going to deal with how high or low your crust is floating. This is used as evidence or related evidence for crustal uplift, because when you remove weight, the crust is going to uplift. Isosity is related to this, and it deals with the idea that as you add and remove weight, the crust is going to be constantly searching for a new equilibrium. The crust is going to be then moving up and down as a result of the addition and removal of weight. We see that there are then going to be some structures related to this. This is looking at isostatic adjustment. Oh my, kind of in general. I was looking for a location for this and I don't have one. I think this is just a general idea. So when you have mountains that weigh a lot that are added onto your continental crust, it's going to result in perhaps some sinking. However, as your mountains are eroded and this weight is removed, isostatic processes are going to uplift your crust surface. Erosion and uplift help to go back to a normal crustal thickness and getting the crust back to where it was perhaps before the mountain was there. But this also means that we're going to discover that mountains can only get so high. When mountains get really high, they add a lot of weight, and that's actually going to sink your crust. Additionally, as mountains get really high, there's going to be more erosion and more mass wasting, which is going to be bringing them back lower to a lower elevation level. There can be gravitational collapse as well, which we haven't even talked about because that's going to be related to the brittleness of the crust you have when things get to be too tall. Horizontal compressional forces, anisosity, and erosion and mass wasting are going to try and keep the crust at a generalized level. And depending upon where you are in the process between mountain building, mass wasting, and erosion and anisosity, it will determine exactly what your average crustal height or what your crustal height is at the moment. In mountain building, it tends to be relatively tall. When a lot of mass wasting and erosion has happened, your crust tends to be less thick. I'm going to go back and try this again. I'm apologizing. The reason we're having a recorded lecture is I am sick, and I should also point out I'm clearly not thinking super straight as I explained this to you guys. So we're going to go back here for a moment. We have volcanic islands forming due to a subduction of your oceanic lithosphere, which is causing melting as the one plate subducts under the other. And that melting is going to result then in magma that is then going to come up through the crust, up through the lithosphere, causing the construction of volcanic islands. We got this one, right? Volcanic islands are happening because there's a subduction of one oceanic plate under the other, which is dealing with some partial melting, which creates magma that comes up and forms volcanic islands. Great. Andean type mountain building is going to be a little bit different. This is going to happen on your overriding plate. So this is going to happen on the plate that is not subducting, but that is a continental plate. Your magmatic activity here is building continental volcanic arches, not oceanic ones like we just looked at. The crust is going to become thick as a result, and this thick crust is going to be a mountain, related to the idea of thickness that we just talked about with viscosity. It's going to tend to happen on passive margins prior to the formation of a subductive zone or on active margins after the formation of a subductive zone. Continental volcanic arch is going to form, so this is going to be on the continent itself. Because your oceanic lithosphere is descending, partial melting is occurring, magma is being produced, and instead of forming a volcanic arch, you're forming a continental arch because you have a continental plate, not an oceanic plate. Batholiths will form. Accretionary wedges can form on the subducting plate. They will then be brought in, and that will be like an island arch being brought in, but it is not quite the same structure. And that's what we see here. So you have a subducting plate, the continental lithosphere is next to it. As your oceanic plate subducts, it's going to create a lot of magmatic activity, which is going to create the structuring of mountain building. And then we can have these collision mountains. This is going to happen where your island arcs that are forming are going to be brought to the continent, and they're going to become part of the continent. So it looks like this. You have microcontinents that are formed. They are then going to be brought to the continent where they become part of the continent. They are plastered on, or they are accreted on to the continent. And instead of descending with the subducting plate, they don't descend or subduct because they are more buoyant than the oceanic lithosphere, because they are continental lithosphere. So they're going to become part of the continental crust. I hope this makes more sense. I apologize for being a little scattered with this at the moment, and I appreciate your time. This is the end of chapter 10.